So today we're going to apply what we did with the pH equilibrium last time to liquid-liquid extraction techniques. So this is not used on every analysis in forensic science, but it is a technique that we need to review from organic, because y'all did some liquid-liquid extraction. I think it was an ether extract and water. And so ether is not the only solvent we can use. There's other kinds of solvents. Any solvent that will strongly separate from water would be a candidate. So probably not something like methanol, right? Because methanol is miscible with water. So you're not going to do liquid-liquid extraction with methanol, but you could do it with, say, ethyl acetate or chloroform ether, as you did. Okay, so here, this what's going on? Well, the extraction removes the analyte from the sample phase or matrix. And so you can extract your analyte and leave behind the materials that are not forensically relevant. So that's what our goal is. Sometimes that sample phase or matrix needs to be destroyed, and that's called digestion. This can also remove it from like solid matrices. So if you're trying to do a trace metal analysis, sometimes you have to dissolve the metal, and so that's another way of saying digestion. So you can put a metal in a strong acid like nitric acid, and it will react with that metal, oxidize it. You have to do this in a hood because it typically produces a lot of NOx gases, nitric oxide, nitrogen dioxide, and so on, toxic gases. But you can pull those metals out and do a trace metal analysis. Or glass. Glasses are really hard to do because glass really doesn't dissolve very well. So glass would be a very difficult sample to digest. You probably need to pick a different technique to analyze glass. They make very aggressive digesting equipment. Some of it is microwave assisted. So you have these Teflon pressure cells that you put in the microwave oven. It's a lab microwave oven, and you use the microwave energy to drive heat into the system. It goes through the Teflon and heats up the liquid inside. Those can be quite dangerous if you don't follow the procedures, because when you put something in a microwave, especially if it's in a sealed vessel, you're heating a sealed container and those can explode. That was my first experience with the microwave. My friend, I was in the after school, you go over to your friend's house, your mom's working, and so I'm at his house. We're playing video games. The video games, yeah, it was Space Invaders for real on the Atari. Tick 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 tick. And so we're in there, and I was playing Space Invaders with Mark, the older brother, and Nathan was in the kitchen, and we heard the microwave going. And then we hear the door open, and then we hear him scream, "Ah!" Yeah, he had put an egg in there just to see what would happen. Microwaves were new. We didn't even have one in my house. So he opens the door, and the vibration caused the egg to explode. And it was cooked inside, right? And so a hot egg hit him in the face and went all over the wall and everything like that. And he's screaming, looking at his face. And we run in there, and he had little red marks. It looked like he had chicken pox. And so what did Mark and I do? He was okay. I guess he could have been blinded, but he wasn't. So, if you're not permanently maimed, then it's a good laugh, right? So, yeah, be careful heating closed containers. But, yeah, microwave digestion is a really good technique for destroying that sample matrix. And then we can use headspace analysis. There's natural partition between vapor and liquid phases, or aqueous and vapor phases. So this can happen very well if you're studying bodily fluids and you want to do like a fatty acid analysis. So we did this studying the effluent of cow manure in like a landfill to collect the biogases. And so when I was at West Texas A&M, the well-funded research at West Texas A&M, being a rural school and an ag-based school, was all agricultural. And so we had some projects where we looked at the fermentation and digestion of manure to produce biogases, primarily methane. And we wanted to see what kind of corrosive or sulfur-laden gases were in that. Because if you're going to use that for natural gas heating purposes or electricity generation, it's the small amounts of sulfur compounds that are going to corrode your equipment. And so we wanted to do some research on how efficiently those digesting liners and so on would work. So we had the fatty acids in that, and we wanted to see what kind of content of the different fatty acids there were. So if you protonated those, in other words, you put a drop of hydrochloric acid into that solution, you protonated all those fatty acids. And now they were no longer very soluble in water, and they came out of solution. It was dramatic. You could have the little beaker, and it had kind of a smell to it, you know. I mean, it was poop juice, you know, right? But you put one drop of hydrochloric acid in there, and I mean, it takes your head off. It smelled so bad, and it was you're protonating all of those organic acids, and they come flying out of solution. And so this is what we're doing. We're doing headspace analysis, and so we can put that in there, put it through the septum, protonate those acids, and then pull a gas. In a gas-tight syringe, we could pull a sample of the headspace and put it on the GC, and then we could get the different profile of the fatty acids. Now, fatty acids are things that you smell when animals are decaying because of all of the fats and so on. They start getting oxidized and they turn into fatty acids. And you're very familiar with some of these. Like, I forget which number of carbons it was because it was a while ago, but like I do remember butyric acid. Butyric acid is the fatty acid that's in vomit. And so that's like pure vomit smell. And then a different number of carbons was BO, you know, and so it was really weird. It's like, that is like a beaker of BO. I mean, your eyes would water in this lab. So we kept everything in the hood. We worked with sulfur compounds too. So we bought some sulfur compound standards like methane thiol, which is the smell they add to natural gas lines. So the natural gas line the natural gas doesn't have any smell. They put a smell in there so that you could detect a leak. And we had a bottle of the pure smell. So I told the student, I said, do not drop that bottle, do not break that bottle, do not spill that bottle, because we will have the fire department searching the whole building for a natural gas leak. And there isn't a natural gas leak. You drop the bottle of smell and everybody's going to think, oh my gosh, we have to evacuate the building. There's a natural gas leak, when there wouldn't be. So anyway, some headspace analysis stories. You can use pH to drive things into headspace or to keep things in solution. And so that's a little bit of what we're talking about today. We use this Raoult's law. Again, the vapor pressure of the analyte is proportional, or is proportional to the concentration of that analyte times its pure vapor pressure. And the X is the mole fraction, so that would be the concentration in terms of moles. And then Henry's law, some things are not ideal gases, or are ideal solutions. And so you have a different proportionality. Instead of the pure vapor pressure here of the substance, like this ethanol, pure vapor pressure, you might have, if this is water, you might have a Henry's law constant for that. And that can be, K can be greater than the pure vapor pressure or less than. If you want to know more about that part, take PChem 2, because that's what we study. Okay. So now let's talk about the hydrophilicity and hydrophobic nature, or lipophilicity. For drugs, fat solubility is just as important as water solubility. And so we can use the octanol water partition coefficient as as sort of the gauge of how fat soluble something is or how water soluble is. So octanol acts as the mimic of your fatty tissues, and water acts as a mimic of your blood. So blood, that's a funny looking bee, just a minute. And so if you want to know if a drug is going to go into your fatty tissues or stay in your blood, this octanol water partition would tell you that, because what we're looking at is we can mix, you can put your substance here, the analyte, into a sep funnel with octanol and water, mix it up, wait till it separates. Then you can pull those two fractions out, and you can sample the aqueous phase, you can sample the organic phase, and the concentration in the organic phase over the water phase. It gives us this partition coefficient. And so if it's greater than 1, it's fat soluble. If it's less than 1, it's water soluble. As you might imagine, this can be lots of powers of 10, and so a lot of times you see in the literature log P. And so it's the log base 10 of P. It's telling you how many orders of magnitude it is in terms of octanol or fat soluble versus water soluble. And so then let's get into the liquid-liquid extraction. So here's this. What's that? Okay, and so we're looking at liquid-liquid extraction, and we're going to separate a sample containing naproxen sodium and codeine HCl. Okay, so step one is always to get more information, and here's some of the information that I need you guys to know. So like this is knowledge that you need to cram into your head. Okay, we have two ways of describing these substances. This one, naproxen sodium, and this one, codeine HCl. So these are solid substances in this form. And whenever you see this sodium, that tells you that this is an acid. And so remember, an acid can be HA, or in this case, it's Na plus A minus. So the naproxen is an acid. Whenever you see naproxen sodium, it's the naproxen anion paired with a sodium cation, precipitated out, and that's the substance that's in this formulation. What about the codeine HCl? Whenever you see this, it tells you that this is a base. And so the bases can be B, or it can be BH plus in aqueous solution. If you want that to precipitate out, you need the counter ion, Cl minus. And so that's the codeine HCl is the salt form of the codeine. So those kinds of things you have to just know. If you see something sodium, it's an acid. If you see something HCl, then you know it's a base. So step one is always to get more information. So we can look these things up in the Merck index. So we see there's the naproxen sodium. It's just showing us the naproxen piece. And here's the codeine piece. And here's the HCl part. You see this right there. And that's a base. And here's the log P. So that's the water partition, the octanol water partition. So it's 3.2. Remember, this is the log of P. So that means it's like 1,000 times more soluble in fat than it is in the water phase. Okay. Here's 0.6. So it's about even in terms of its solubility in water or in fat. And so this is why it says water solubility, it's insoluble, because again, the log P is 3.2. Okay. Let's see what else. We have the solubility in ethanol and chloroform and ether. So 1 to 25. So that means 1 naproxen sodium for 25 water, 1 part to 1 part. And these are typically mass solubilities. And so it would be 1 gram to 25 grams of water. 1 gram of I'll say HA to 25 grams of H2O. So that's how you would read that. If you go to more than 1 gram and 25 grams of water, it would precipitate out. So this is the saturated solution. If you make the saturated solution, this would be the concentration of the liquid above that. Okay. Chloroform, it's 1 to 15. So it's more soluble in chloroform. You see how you can put a gram in 15 grams, or the other one you have to have 25 grams to get 1 gram into solution. Here's 1 to 40, not very soluble in ether compared to the other two. So here you need 40 grams of ether to get 1 gram of this compound in the solution. Does that make sense, these solubilities? Okay. Look down here at the codeine HCl, at 1 to 20 in water. Oh, you guys should have raised your hand and said, why are you calling ethanol water? This is not water, this is ethanol. Yeah, it's insoluble in water. Okay. Down here, it's 1 to 20 for the codeine HCl, 1 to 180 in ethanol, and 1 to 800 in chloroform. So not very soluble in chloroform at all. You need 800 grams of chloroform before you could get 1 gram of this substance to dissolve. That's a lot. I mean, 800 grams might be, 800 mils if it's like water. It's not. It's more dense than water. But still, that's a lot to get 1 gram in. And so this is the biggest difference. So we would probably want to use chloroform as our organic phase, right? Because already the chloroform is going to favor the naproxen sodium over the codeine HCl. Okay, so if you just put those in contact with water or the aqueous solution, the naproxen sodium is going to go into the chloroform layer, and the codeine is going to go into the water layer, and you don't even have to worry about the pH. It could just be regular water, and that would happen. But the pKa values are very different. So let's look at those for a second. We got this pKa of 4.2 for the HA form, okay? And this is a pKa of 8.2, and that's for the BH plus form. So these are pKa's. So they're for the acid. And even though I have a basic substance in the codeine, if I protonate it, it's now an acid, right? It's the conjugate acid of the base. So we're thinking in terms of acids. We can put it on this scheme where we have the pH speciation. And this is what we did last time at the very end of the lab, trying to draw the species and which one is going to be aqueous, which one's going to be organic. And so if we're below 4.2, this is what we have. We have the BH plus. Let's see, which one was the 4.2? I want to make sure I get the right row. The naproxen was the 4.2. Okay, so this is the HA. Okay, and this is the BH plus. And I mean, you don't have to worry about the HCl. As soon as it goes into solution, it keeps the H plus and the Cl goes somewhere else. Water takes it away. So it's really focusing on the substances, not the counter ion, the HCl. The Cl part, Cl minus, is floating around in water. Okay, and then if you wanted to go above 8.2, now you've deprotonated the base. And so this is just B, and this is the A minus. And this is aqueous. So all of the ionized pieces are aqueous. And this is in the organic phase, and this would be in the organic phase. Okay. So do you see which regions of pH would be good for separating these two compounds? If we're doing a liquid-liquid extraction. And the pH applies to the aqueous portion in that SEP funnel. We add a little acid or add a little base. We add some acid, we can make it a low pH. We add some base, we can make it high pH. So where do we want to tune the pH to where we drive one into the organic phase and keep the other in the aqueous phase? Yeah, we have two choices. We could go with an acidic solution, and if we're in the acidic solution, then the naproxen would be in the organic phase, and the codeine would be in the aqueous phase. And so we've separated our two compounds. And then we could go analyze them in some way. We could do a spectroscopic measurement on the pure naproxen or the pure codeine. That way our spectrum would be nice and clean. We don't have a mixture. Or we could go above 8.2, and the naproxen would be in the aqueous phase as the anion, and the base would be in the organic phase as the neutral. So neutrals are in the organic phase, and charged things, ionized things, are in the aqueous phases. That's what you have to know. That's the trick, and it's that simple. Let yourself get it. We're not doing any ice table calculations. We're just going way beyond the pKa's, right? If we're sitting right at the pKa, it's 50-50. It's 50-50 A minus and HA, because that's where when the pH equals the pKa, we're halfway to the end point. We have half protonated, half deprotonated. So we don't want to be right on the pKa. We want to be past it by at least one number. If we can get one whole unit past it, that's a power of 10, because these are exponents, right? So if we go to pH of 3.3, then it's like 10 times more of one than the other. All right. So which one of these makes more sense, though? Let's go back and see which one prefers the organic phase. Remember, the naproxen really liked the organic phase. And so let's drive the naproxen sodium into the organic phase. And so that was the naproxen in the organic phase. So it would be this one here. So we would want to be below pH 4.2. So that's how we would decide if we were going to use the low pH or the high pH. We would choose the low pH because the naproxen, the HA, was more soluble in the organic phase than the codeine. Now this chart here, this codeine, I think these numbers, these solubility numbers, are for this HCl form of that. So anyway, but yeah, we would want to do the low pH because the naproxen is so much more soluble in the chloroform. The log P values are very different, so this leads to very different chloroform solubility. So essentially, the concentration of naproxen in the chloroform is 1 in 15. In water is essentially 0, so that's like infinite solubility in the chloroform. And then the codeine is 1 to 800 on top and 1 to 20 on the water, so it's 0.025. So this would be a really good solvent to partition these two. We place the substances in the SEP funnel with the chloroform in the water. We adjust the pH of the aqueous phase and shake, and then we get the good separation. So here's a universal extraction scheme. So if we have an unknown mixture, some sort of powder, and we want to separate all of these different things, these are the classes of extracts that we would get. Okay. So we could just take this unknown, this sample mixture, and we could pick our favorite organic phase. Chloroform may not be your favorite. Maybe it's ethyl acetate or something like that. And we adjust the pH of the aqueous layer to less than 2. So we put maybe some hydrochloric acid in there and dissolve that sample. And then we extract it. We put it in contact with an organic phase. And then do you see what let's just say that it's chloroform. So we have the lower phase is the organic phase. And so the organic phase goes here and the aqueous phase goes here. So when we say we extract it, we put it in the SEP funnel, we shake and vent and shake and vent. And then we draw off the organic phase and set it in one beaker, and we draw off the aqueous phase and set it in another beaker. And what's in those? Well, the organics are the acids, which are protonated at low pH. They become neutral at low pH, and so we get the organic acids and the neutral compounds that are not pH active. So like things that have amides, proteins, stuff like that, that are still soluble, because again, this is a liquid extraction. So if it's not soluble, it's been filtered off and it's on the filter paper. And so then we have in this organic phase, and then over here in the aqueous phase, we have the deprotonated bases. So, the protonated bases, which are now ionized, and they're in the aqueous phase. And then we have water-soluble compounds. So that's in the aqueous phase. Now, we put that into a SEP funnel, and we put in fresh organic phase. Okay. And we shake and shake, vent, and then we separate. And so then this aqueous phase, so we put that in with fresh organic, and we adjusted the pH to 9. So it was a pH of 2, and now we move the pH up to 9. And so those weak bases, those organic bases that have a pKa that's between, say, 3 and 8, those would all be then protonated and go into the organic phase. Okay, and the ones that have a high pKa would be in the aqueous phase. So the stronger bases would go to the aqueous phase, the weaker bases would go to the organic, and we've now separated our bases. And we can then analyze those. We've cleaned it up. We've got organic weak bases and amphoteric, things that are both have like an amino acid, right? It's got a base on one side and an acid on the other. And so it would go into this organic phase. And then we have this aqueous phase. We would adjust it to pH 11 and put it into the SEP funnel, and then we put fresh organic in there. And now we're at a really high pH, so the strong bases, organic strong bases, would go into the organic phase. And then the aqueous would still have the water solubles and metals. Okay, so these things would have been soluble the whole time and stayed in the aqueous phase the whole time, no matter what the pH was. Okay. Any questions on this? Some of those metals might form hydroxide precipitates when you go up this high in pH, and that would also be something that you could filter off. All right, so that's the aqueous layer. We kept adjusting the pH and extracting organics out of the aqueous layers that got past this initial screen. Now let's take this organic phase and we add in fresh aqueous. So that goes in here. The organic goes in here. We shake it, extract it, the aqueous and the organics here. This is the separation. The aqueous contains the strong acids because, again, these were protonated at a pH less than 2. And then when we brought the pH up to 6, then those were deprotonated. So they're pretty strong acids, and they go into the aqueous phase because it's A-. They've been deprotonated at a pH less than 6, so they're acidic compounds. So we have the strong acids and the salicylic acid, easy for me to say. And then you got the really weak acids and neutrals in this organic phase that are still protonated at pH of 6. Okay, then we can adjust that pH of 10 and with this fresh aqueous layer here. And the organic phase goes in here, shake and vent, and separate. And the organic has things that are neutral organic compounds, and I guess meprobate is one of those examples. But yeah, the neutrals are coming all the way into organic layer. They never go into the aqueous layer. And then we have the really, really weak acids, such as phenobarbital. So, yeah. And so this is... we have now 6 different groups. So with a lot, we've done 1, 2, 3, 4, 5. So we've done 5 different extractions, and we have 1, 2, 3, 4, 5, 6. So 6 different partitions with 6 different types of analytes in it. And again, this is a universal extraction scheme. This would be this is really just a sketch of the scheme. You would have like a procedure to follow that tells you how much to use and all of that. But this is how you separate some of these analytes and get them purified enough to do an analysis. If you were to run, let's say, an FTIR on the mixture up here, it would be unintelligible. You'd have so many peaks from so many different compounds. But here you can run 6 different FTIRs and have a much cleaner spectrum. Okay, so that's using liquid-liquid extraction. We could also use separations using chromatography. And there's different types of chromatography. Now, you study this in detail in the instrumental analysis course, but we'll just sort of give a quick review over these things. The partition liquid chromatography separates by polarity, and you have 2 common ways of describing this. Let me go back. Normal phase, which really just captures the way this experiment was done originally. where you have a polar stationary phase, typically aluminum oxide. It's a great compound because it doesn't really react with anything. Aluminum is has such a strong affinity for oxygen, and once you make aluminum oxide, it's pretty inert. And so you can put all your organic compounds and everything on aluminum oxide, and they're not going to react with aluminum oxide. But it's very polar because you have all of those metal oxide bonds in that powder. And so the surface of the aluminum oxide is a very polar surface. So if you have something with the carbonyl or an acid group or whatever, it's going to really want to associate with that aluminum oxide. If it's in powdered form, then there's lots of surface area too, so it can really interact with that aluminum oxide stationary phase. Now, if you were to do something that was a nonpolar stationary phase, then that would be called reversed phase. So normal phase is polar, and reversed phase is nonpolar. So those are the two associations you need to make. We also want a very non-reactive surface. We don't want this to react with our substances, and so a lot of times those are silanes or siloxanes or phenolsilanes. So silanes, methyl silanes, and diphenyl silanes. Now, what in the heck is a silane? Well, it's, if you look up here, carbon is in group 4. Right below it is silicon. And so that's what we're talking about. And so it would be the same kind of thing that you would see with carbon with, CH2s, but you have SiH2s. And so this substance it's a backbone of silicon or silicon oxide. And you can put two things on those silicons. Maybe you put a methyl group or diphenyl. What do you think? You put two phenyl groups on there. So these are nonpolar phases. You can make this polymer really long so it doesn't dissolve, and that's a good option for a nonpolar or reverse phase stationary phase. Okay. Now then you have adsorption liquid chromatography that separates by polarizability, or the floppiness of your molecule. So if you have something that's like a CH2 backbone, an organic compound with lots of aliphatic pieces, those are not, the electron cloud around those is not very polarizable. But if you have chlorides or even acid groups, or nitrogens or sulfurs, those add more electrons to the electron cloud. You have non-bonded pairs, and so those are more polarizable. And so you can use a porous stationary phase for nonpolar organic mixtures, things that have chlorides and so on. Then you have ion exchange liquid chromatography, which separates by chelation, which would do aqueous ions. And then you have size exclusion liquid chromatography, which separates by size of polymers. So polymers is typically using size exclusion liquid chromatography, or sometimes they call it gel permeation. Where they shove one polymer through another polymer. So what do you think is going to come out first, right? The big ones. It's the stationary phase has got little gaps in it, and the big ones don't fit in those gaps. So it's a little reversed from what you think. The big ones come through first because they don't fit in any of the pores, and then the little ones get in those pores and get stuck, and so they come out last. And then you have gas chromatography, separates solubility in the stationary phase or adsorption. And again, you can have normal phase and reverse phase for these two. So normal and reverse phases also works for gas chromatography. And adsorption too. Okay. And then we have a technique that's a little bit higher cost, but it's very versatile, and it's super critical fluid chromatography, where it typically uses carbon dioxide, where they pressurize it up to where it's a supercritical fluid, and it's the mobile phase, and it does really well. So let's talk about the simple ones. This is thin layer chromatography, which is this alumina or aluminum oxide on glass. And so you get this aluminum oxide slurry, and you put it on the glass and let it dry, and it's got this nice thick layer. Kind of looks like icing on the glass. And then you can put a drop down here, and we got a little video that shows this, but so I put a drop of the mixture. I stick it in an elution chamber, and the mobile phase goes up, and it drags the compounds in that mixture up across the stationary phase, and you can see where it's wet. And so you wait until the wet line gets up here, then you mark it quickly with a pencil, because then the solvent's going to evaporate and leave your spots there, and then you have your 3 spots. Did y'all do any TLC in organic? Or where did you do it? You said yes. Botany. Oh, that's cool. In fact, that was my experience too. My 7th grade, was it 7th grade? It was one of my middle school science teachers. She had a plant in her room that had green and red leaves. And so she ground up those leaves, and she did column chromatography. So she put the alcohol extract of the leaves up here, and then she started pouring water through, and we could see a green layer from the chlorophyll, and we saw a red layer from some other tannins or something. It was awesome. So we were like, what? Yeah. So that was really cool. This would be if you're like trying to get these layers out in a substantial amount, and then you could do science on those layers. You could analyze them too in the forensics. This would be just a spot test, and there's some spot tests that you have for marijuana to get the different cannabinoids out. So you can do an ether extract of marijuana, put it on here, do a thin layer chromatography, and then you spray a color test on there, and it'll turn those spots different colors. And so then you kind of derivatize it and make it a colored substance. So here's an example from my workshop that I did with the product quality cleaning workshop. And this is our setup for our online, what do I want to say? I lost the, let's go back. So we're just separating the inks in Sharpie. So here we put the regular Sharpie on a slide, and here we have industrial Sharpie. And we have an elution chamber filled with ethanol. Well, it's filled, it's just got a pool of ethanol in the bottom. We're going to put that in there. And we're just going to run this experiment the whole time while we talk. And you guys can watch it happen in real time. So our question was, are these the same, or did Sharpie people just label one industrial and charge us more? Right? So it's a simple experiment. Ah, did it again. Come on now. Where's my mouse? There. Thin layer chromatography slide. And here we have industrial Sharpie. Okay, I'm not going to touch it. And we have an elution chamber filled with ethanol. Well, it's filled, it's just got a pool of ethanol in the bottom. We're going to put that in there. So we did a line. We're just going to run this experiment the whole time while we talk. And you guys can watch it happen in real time. You can see that ethanol line, the eluent is pushing good, huh? Up, and it's going to interact with that black stripe, and it's going to push those compounds up, and then we'll stop it close to the end of the lab. We had like, and you can tell that the industrial Sharpie and the regular Sharpie are fairly different. Yeah. Oh yeah, let's pull the Sharpie system. Someone said, "Hey, you better check the Sharpies." I was like, "Oh yeah, better check." And run into our ears. So. The thing that you need to do when you pull these out is immediately mark the solvent front with a pencil, not a blue pen like I did. So this is the industrial Sharpie, and notice I've marked the solvent front.
And in chromatography, that's very similar to the retention time, is the ratio in centimeters or millimeters from this point to the solvent front. And so this dark line right here will always come out at that ratio. So it will have a ratio of about 75%.
So it's repeatable.
So 0.75 of that distance will be this particular substance's retention time or distance traveled in thin layer chromatography. And likewise for this blue line, it might have a travel ratio of about 0.25.
And analyze it.
And so that number is repeatable. And so you can then describe these compounds with their travel distances, and that's a repeatable number. And this was the regular Sharpie. It's much more colorful, and it has again this blue peak is not very well retained, or is retained well by the stationary phase,
so it's
and
polar.
The yellow is kind of hard to see today, but it's right there. And so.
Another neat setup. Anyway, we worked hard on that. It was anyway. So here's a neat one. So this is chromatography, but the data you get on chromatography looks like a chromatogram. So if you were to turn this into a chromatogram, this is what we would have. Oh, not that. This. Come on, there it is. So if you were to sort of draw a total chromatogram on here, every one of those compounds would be a peak. And the more spread out it is, the more broad the peak. But if you had a selective chromatogram, like just the blue species, this is what it would look like. And so the bottom one would be what we call the total chromatogram, and then the blue one would be the species specific chromatogram. With mass spec, you can imagine you can sit right on a mass and you don't see it if it's not there. But then you're coming along and then the molecule that has that mass would come out and you would see that peak come up. And you could have all kinds of junk coming through and hitting the detector, but you're only looking for that particular mass. And so you would just ignore all of those other signals until you see that mass. So that's why GC coupled to a mass spec is the gold standard. I mean, and in fact, you get 2 forensic credits, if you want to call it that, right? You've got the retention time of the compound. That's a repeatable thing related to that compound. And then you've got the mass data on that compound. You've got its fragment patterns, you've got its molecular ion peak. And so you're getting 2 analyses out of a hyphenated technique, like a gas chromatograph and a mass spec. There's lots of detectors you can put on a chromatograph. A lot of them are like thermal conductivity detectors. They don't really give you anything tied to the identity of that compound. It's just how that compound affects the heat that's coming off of a little hot wire, electrical wire. So if that the conductivity through that electrical wire will change depending upon the gases that are around it. And so you've got this hot wire and the gases are going past that hot wire, and when the gas changes from the mobile phase to some other compound, the conductivity of that wire changes, and so you could just plot that. So you get retention time data from a thermal conductivity detector, but you don't get anything that's really connected to the identity of the compound except for the retention time. And then we have, yes?
So were you able to determine just using that if they were saying the same thing? They look completely different.
Yeah, it's completely different. That was the conclusion, that they really are different. The industrial Sharpie has it just has a different pattern of compounds. So it really is a different formulation. And notice that a lot of the black doesn't move. Like where we marked it, that's still dark black. And so these are the minor components of those pigments. A lot of it is carbon black. It's just charcoal that's ground up and put into the formulation of the ink. And the ink has some sort of organic solvent. I don't recall what their solvent is, but it just suspends those carbon black particles and gets them down onto the surface. And then they also have, we've analyzed Sharpie quite a bit because we use it to test cleaning equipment. So if you're testing an ultrasonic tank or some sort of cleaning equipment or some sort of solvent method, we mark up a frosted or microscope slide with Sharpie. and see if that solvent blend will clean the Sharpie. It's a good test soil. And you can take photographs and sort of measure how dark the surface is to see how clean it is. So that's a really good test soil. Like if I've got an ultrasonic tank and I want to see if it's really operating, they can still make noise and not actually be doing anything. And so there could be an electronic noise coming out of that thing, but it's not actually making cavitation under the water. So you can use the Sharpie test and a foil erosion test, all these different kinds of tests to see if the ultrasonic energy is really there. There's another one that we're very familiar with now, the COVID test. These are enzyme-linked immunoabsorbent assays, or ELISA tests. So an antibody, and that's just one example. An antibody binds with an antigen and forms an antibody-antigen complex. So all of them are based on that kind of selectivity. The compounds are so incredibly large. These are large enzymes, and so we have to resort to cartoons. And that's what this is. This is a cartoon. This is the key over here. This is the antibody, this Y-shaped structure. This is the drug or some sort of substance, and it's linked to another enzyme. So this enzyme then can change this substrate from clear to a color. And so this is one way to do it. If there's a lot of drugs there, then you'll see a color change because this will not be down into the antibody. But if it goes down into the antibody, it's blocked and you don't get a color change. And so there's lots of ways to arrange this and lots of different, different schemes. Sometimes this is attached to this cell, the card or whatever, and then the antibodies are floating around. And so there's, again, I wouldn't say infinite variety, but a dizzying array of ways to do these ELISA tests. How many people have a COVID test and saw the color changes and all of that stuff? I mean, it's kind of interesting. Why do we need a control? Why is that important? Yeah, and what could make the test not work properly? Problems with manufacturing? Perhaps, but that is less likely than these other things that can go wrong. But it is a possibility. Yes. Storage. What are these things made out of? What is the actual? I mean, this is paper, right? Paper is not. There's no problem storing paper. But look at all of these things. Specifically this guy here, the Y piece, and this piece right here. They are proteins. They are enzymes. They are things that are folded a particular way, and they're temperature sensitive. Okay? When you're cooking an egg, what happens? It's mostly protein. It turns white. Why is it doing that? It's the thermal thing. You're just denaturing those proteins. And they go from a clear viscous liquid to a more semi-solid white substance that's more like a solid gel. It's really not quite a solid, but it's not a liquid either. It's what we call a gel phase. It's flexible, but doesn't really flow. So a liquid will flow, but a gel won't really flow. It might flow very slowly. But notice how it's not quite a solid. A solid has a fixed shape. Does a scrambled egg have a fixed shape? No, right? So it's flexible, but it doesn't really flow like a liquid. So so we don't. If this thing goes in a truck and it's not air conditioned or maintained in some sort of controlled environment, then those enzymes may denature, and then the test won't be valid. And maybe you get a color change and you think, oh, it's a false positive, or maybe it's such that you would never get a color change and you get a false negative. So we have to have that control so that we can see, yeah, the enzymes in this test are still good, and then we can trust that they would work for the thing that they're testing. These are the same kinds of tests we used obviously for COVID, but the same kind of tests we use for pregnancy tests. They're incredibly sensitive, and they're incredibly sensitive at picking the thing that they're made to analyze. So they're made to analyze this particular antigen. So this is the antigen-antibody complex. So this antigen here. And so they can be made to search for particular drug substances. They can be made to search for spike proteins on a coronavirus or on hormones in a pregnancy. So if you those hormones will be present in your urine, so you can pee on a little strip, and if you see a color change due to a hormone that indicates pregnancy, then you've got a positive pregnancy test. I think it's really clever how they do this. They'll put the control like this, so that'll be the control. And they'll put the test like this. So if you have hormone and a good control, you get a positive. All right. If you have no hormone but a good control, you get a negative. And that's really pretty neat. I think it's like chemistry that also tells you something. Like the chemistry is telling you there's no digital readout, you don't need a battery. You know, it's amazing that just the pattern of the enzymes on the thing will tell you positive or negative. And I think that's really clever. These can be automated, and so you can buy these plates. Now you can get like a 24 well plate or whatever if you're doing pipettes by hand, right? And have y'all done those in biochem? What do y'all do those? Yeah, okay. What's the biggest number of plates that y'all did? 96, yeah. But look at this 1536. Can you imagine trying to pipette into this thing? Right. So when you get that big, guess what? It's robot time. You got these little bitty pipettes, and the robots are delivering and setting up your titer lines and so on, and you're doing all of your quantitative analysis. And so in big labs, we had a guy come from the DEA lab, and he was telling the students about his day. And he said, well, in the morning I come in and I set up like 1,500 urine samples that have come into the lab. And then I go do paperwork all day because I got all the reports from yesterday's 1,500 to go through and report those out. And so the instrument's just working hard all day doing the chemistry. That's not every lab, but that is some of the labs. And so when you think, man, I'm going to be in the lab, right? You're going to be splitting samples and putting them in the trays and setting up the robot and saying go, and then going to Excel, and Word and all the databases. So don't let me depress you. Okay, so that we're done a little early, but I'm going to go upstairs and get the tests, and I'll bring them back down. We got some time, and y'all can look at the tests.